the community have been recognized. So I think it's important. It means that the mathematics we are doing, it's valued by the whole mathematical community. And then, of course, there is the personal side. It was a big satisfaction, and also it has given me also the opportunity to do many things. Public lecture for students, so a kind of exposure, and that it's important, I think, because when you get a bit of celebrity, it's also can be used. You can use it for, and that's what I'm trying to do, especially in Italy, actually.
Well, I think that is a perfect point to pause our conversation. We are going to be joined by some of your peers in a moment for a panel discussion. But in the meantime, we're going to play the audience a few little videos. So we'll see you very shortly.
Thank you, Hannah and Alessio, for that engaging and inspiring conversation. We will now hear from Professor Feridun Hamdullahpur, President of the University of Waterloo. As I mentioned at the outset, the Fields Institute is a network of 21 principal sponsoring and affiliated universities and institutions. One of the major universities in this network is the University of Waterloo. Professor Hamdullahpur is a professor of mechanical engineering and has authored hundreds of scholarly publications and supervised more than 50 graduate students. We will also hear from Professor Carlos Koenig, the president of the International Mathematical Union. He obtained his PhD from the University of Chicago. After being an instructor at Princeton University and a professor at the University of Minnesota, Professor Koenig returned to the University of Chicago, where he is now Louis Bloch Distinguished Service Professor in the Department of Mathematics. He is a fellow of the National Academy of Sciences and has spoken thrice at the International Congress of Mathematicians.
Hello, Fields Medal Symposium from the University of Waterloo. We are incredibly proud to be in Canada and at Waterloo, to be here and had the advantages Canada can provide. Having our university in Canada has allowed us to see growth and impact we never thought possible. As the home of North America's only dedicated faculty of mathematics, the Fields Medal Symposium is an important event in our calendar, in addition to its importance to the mathematical community. With more than 40,000 alumni from our Faculty of Mathematics and 5 decades of expensive fundamental research, including pioneering computer science teaching and research, we have seen the far-reaching implications of mathematics in our world firsthand, and it's only getting started. Expansive growth in technology and understanding the foundations of our world are shaping our society, and all of it is rooted in mathematics. And mathematics is having a tremendous impact, allowing us to unlock the power of information. Some impacts we see directly, such as using AI and data to detect cancer earlier, and some we don't see at all. But the power of math is everywhere. Right now, we need more ideas, more perspectives, and more collaboration to continue to this march forward in the area of mathematics. And I know that efforts is at the heart of John Charles Fields and the Fields Institute. Having the Fields Institute right here in Canada is a true asset for our nation that fosters the growth and excellence in scholarship and mathematics. There are so many avenues of connection between researchers, students, institutions, industry, and society that we can foster and further strengthen. Entire industries have started from building these connections that lead from essential, fundamental research to practical applications. We have seen this at Waterloo with companies like OpenText that stem from a research project at the university, only to be spun out into a globally recognized leader in information storage and distribution. I know through the continued efforts of the Fields Institute and its network of principal sponsoring and affiliate universities, we can build off of these connections for an impact we could only have once imagined. I would also like to take the opportunity to congratulate Professor Figali, who is being celebrated at this year's symposium. I hope that his achievements serve as an inspiration for for so many young and aspiring members of today's audience. Congratulations to the Fields Institute for your continuing efforts to promote the collaboration and excellence in mathematics research and application. The University of Waterloo is proud to be a partner and part of the symposium. It does so much to connect and inspire students and researchers around the world. With my best wishes, have a great symposium, and thank you.
Hello, everyone. I am Carlos Koenig, the president of the International Mathematical Union. It is a pleasure for me to take part in this year's Fields Medal Symposium honoring Alessio Figali. This is particularly rewarding for me since Alessio's research has much in common with my own work. The Fields Institute and the International Mathematical Union, IMU, have a long and close relationship stemming from the fact that J.C. Fields, for whom this institute is named, was the initiator of the Fields Medal Award, the flagship award of the IMU, which is now recognized by many as the most prestigious award in mathematics. J.C. Fields was the lead organizer of the International Congress of Mathematicians, ICM, held in Toronto in 1924. After the Congress, there were unspent funds that had remained. Fields, who was very concerned with the lack of an award for mathematicians of the stature of the Nobel Prize, thought that it would be a good idea to use these remaining funds to endow a new prize in mathematics. It was planned that he would advance this idea at the 1932 ICM in Zurich, but he died in Toronto in the summer of 1932 before the Congress. In his will, he left a substantial amount of money for the purpose of establishing the prize, and this money, added to the leftover funds from the 1924 Congress, endowed the prize after Fields' proposal was accepted by the 1932 ICM in Zurich. The first Fields medals were awarded at the ICM in Oslo in 1936. Before his death, Fields explicitly asked that the award not be named after any person or place, but this wish was overruled after his death. Fields' conception of the awards was that they should be in recognition of work already done and an encouragement for further achievement, in contrast with the Nobel Prize. Following his wishes, the Fields medals are now awarded every 4 years on the occasion of the ICM to recognize outstanding mathematical achievement for existing work and for the promise of future achievement. Currently, 4 medals are awarded to candidates under the age of 40. Over the years, the trust fund established by Field has had to be periodically supplemented, and it is still significantly underfunded. The discrepancy in 2018 was made up by the University of Toronto and the Fields Institute. Let me conclude by thanking the Fields Institute for their collaboration with the IMU, by congratulating Alessio Figali for this award, and by wishing you all a productive symposium.
Thank you, President Hamdulapur and Professor Koenig, for speaking on the Institute's relationships and collaborations, both with our principal sponsoring universities here in Canada and with the wider international mathematics community. Building on the previous conversation between Hannah and Alessio, let's open up the discussion now to include some very distinguished mathematicians from around the world. Joining Hannah and Alessio, we have Robert McCann, who's a professor at the University of Toronto and a fellow of the Royal Society of Canada, Cedric Villani, who is himself a Fields medalist in 2010 and currently a member of the Assemblée Nationale, Maria Colombo, who is a professor at the École Polytechnique Fédérale de Lausanne and who was a student of Figali, and Ingrid Dobeshi, who is a professor at Duke University and a former president of the International Mathematical Union.
And now we come to one of my favourite moments of the evening. Alessio is joined in conversation with a number of his peers to retell some of their greatest adventures, I think. Now, earlier on today, I went on Twitter to ask what the collective name should be for a group of world-class mathematicians. And there were some very good suggestions. Someone said a sum of mathematicians, which I quite liked. There was also a bracket of mathematicians, which I think was my personal favourite. Of course, if you were all a group of geometrists, it would surely be a Euclid. But I think we're going to settle on the most popular answer on Twitter today, which is a proof of mathematicians. So I hope you're happy with that as your collective noun. Now, I have to tell you that we were going to be joined by Professor Ingrid Dobushi this evening, who I'm sorry to say has been called away by a family emergency. We wish her and her family all the very best. But that said, we still have a stellar cast in this evening's Proof of Mathematicians. First, we are joined by a man who was described by the New Yorker as the Lady Gaga of mathematics. What a title. Cédric Villani is a French politician and mathematician working primarily on partial differential equations, Riemann geometry, and mathematical physics. The Fields Medal in 2010 and was the director of the Sorbonne University's Institut Henri Poincaré from 2009 to 2017. Now, Cédric Villani was also the PhD supervisor of Alessio, which in many ways makes him the grandfather advisor or grand supervisor, that's what I'm calling it, of our next panellist, who in turn was a Alessio student. And I should tell you that Maria Colombo is a formidable mathematician in her own right. She was awarded her PhD in 2015 with a thesis on flows of non-smooth vector fields and degenerate elliptic equations. She is currently a tenure-track assistant professor of mathematics at EPFL, where she leads the chair of mathematical analysis, calculus of variations and PDEs, and she has a number of prizes along the way, including the Miranda Prize in 2018 and the Ia Picino Prize in 2016, which I know I pronounced wrong, haven't I? I even checked in with you in advance and I've got it wrong. I'd also like to point out how impressive her chalkboard is. I know that Alessio said he's not competitive, but I think Maria's winning on that one. Now, last but not least, we have Robert McCann, who has been a professor of mathematics at the University of Toronto since 1998. And along with his collaborators and peers worldwide, Robert McCann has led a renaissance in the theory of optimal transportation, helping to over the years into one of the most vibrant and exciting areas in mathematics today. He's also been elected to fellowships in a number of learned societies, including the Field Institute, the American Mathematical Society, the Canadian Mathematical Society, and the Royal Society of Canada. Now, Robert is also a collaborator of Alessio. So we've got a line here then from Cédric through Alessio to Maria, and then from Alessio to Robert too. Is that kind of thing usual in a sort of collaborative environment, Robert? Do research partnerships tend to take this sort of shape? Or what would you say, a tree? Or what do you think?
Well, I mean, I'm also a former collaborator of Cédric's. And you know, Maria is also an academic sibling of Alessio's in addition to being a student, so there's a bit of incest going on in this tree. It's not a tree because you can have cycles, right?
Of course, it's a fully connected graph in many ways, right? Rather than anything else.
It's a graph, maybe not fully connected, yeah.
Close. Alessio, a question actually came in from YouTube about this idea about the methodology and how important it is in passing on mathematical knowledge in a sort of intergenerational building of mathematical frameworks. What's your view on this idea of mathematical genealogy?
Well, I mean, I think the resources are very important for shaping the mathematical research of the students. So of course, this genealogy, you see where people come from, and I think it's really what they do in the research. So in my research, I think I see a lot. If I look at it in retrospective, I see a lot both of Luigi and Cédric. So all these, three connected. In fact, there is more than just mathematical blood, but really they influence the kind of way of doing mathematics, the idea, the inspiration. It's very important. I think that's why I think the advisor has a very important role in the career of a mathematician.
Yeah, very much so. But of course, it's not just the advisors, it's collaborators too in many ways. And Maria, there was a question that also came in on YouTube, which said, many people view mathematics as an individual pursuit. Do you feel the same, or do you feel that mathematics is better as a collaborative effort? Now, we can't quite hear you, Maria. I wonder.
Are you muted?
Potentially. Are you muted? I mean, that's the catchphrase of 2020, let's be honest.
Oh, I'm sorry.
There we go. We've got you. Yeah, what are your thoughts?
Yes, I see really as a collaborative environment. Also, I grew up somehow in the same school where Alessio developed himself, and I see many common traits in between very different people. in the way they do mathematics, in the way they discuss mathematics. Also, I think Alessio somehow never left the first problems that his advisors proposed him in some way, even though he developed towards other areas as well. And this is from somehow the mathematical point of view, but also from the human point of view. I see some common aspects in the way people interact with each other. For instance, one thing that always impressed me is that both the door of Luigi Ambrosio and the door of Alessio were always open. And they were both, when I was a PhD student, even at the very first experience, they were both answering my emails within the day normally. And this is something that is not so obvious in other communities. And I think it has a common root in a way of perceiving mathematics and of doing mathematics that is common to a certain school, usually.
Yeah, I think that sounds important. Cedric, as Alessio's PhD advisor, how was he as a student?
Advisor to student relation is always extremely important, and it's always the best situation when your student becomes your collaborator at some point. This has occurred to me with several of my my students. Let me first mention that it's very true what was said by Robert and by Maria. The relation of genealogy in scientific terms has a lot of influence on the subjects, but also on the style of mathematics that you use, the way you see problems and so on. And it's very important that Alessio was both student of Luigi Ambrosio and myself, and it's very clear in his work the influence of the school that I represent and the school that Luigi represents, plus his own specific traits. Similarly, I'm used to say that I was a student of four people. There was Pierre Lullion, there was Yann Brenier, there was Michel Ledoux, and there was Eric Carlen. And I can see the influence of the four people in my work, plus some of my own specific traits. As a student, Alessio, let's say the first characteristic was it was a very international adventure from the start. He was my student in Lyon. At the same time, he was working with Luigi Ambrosio in Pisa. And then very quickly, it also developed into a lot of collaborations worldwide. And this international feature is very essential in mathematics, data science, at the moment in which governments everywhere in the world are kind of shrinking on themselves and trying to put barriers towards other governments. It's very important for us to recover how international scientific research is. Second characteristic of Alessio as a student was the speed, amazing speed at which he was working. And there are anecdotes which I used to tell to other people of me, suggesting a problem to Alessio in the morning and having the solution in the evening. And there are many stories about this kind of behavior of Alessio. I'm sure Robert has a couple of those also. Third thing with Alessio was the ease of communicating and always going to people. Now, Maria was saying it's so great to have the door open when for the office of Luigi or Alessio, but also these are people that go towards the people and always ask, which problems are you working on? What can I do? A very, always acting together, acting to find new problems. And the fourth characteristic with Alessio is his ease about reading and absorbing entire fields of mathematics that I have never seen in any other young mathematician. Like he read my 1,000-page book on optimal transport as if it was a Dostoevsky novel, and pointing to me all a number of mistakes there. But also whenever there was a subject, I told him, this is in the book of Struck and Vardan, for instance. And then a few days later, he comes back and says, oh, I have read the entire book, and here is the blah, 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 blah. And this absorbing mathematical sponge style was also very much striking.
What a response. And I say I won't come to you for fear of embarrassing you too much. So instead, Robert, let me come to you. I mean, all of you work in a very similar field, and I wondered if you could just give us a bit of an overview about how much that field has changed and developed over, say, the last decade or so, and where you see it heading from here going forwards.
So I mean, let's go back 3 decades to when I started. So when I started, I was still a PhD student when my own advisor brought the work of Jan Brenier to my attention. And that was really pivotal work at the end of the 80s and the beginning of 90s. And it was when the Renaissance started, more or less. So it was the first connection that I've seen between optimal transport and partial differential equations, which is really the field that Alessio has continued to work in. And it developed, I would say, rather slowly over the 90s. And so Cedric, so I was working in it myself. I used it a lot in my thesis.
Yes, and Robert and I met in 1999, I guess. So already more than 20 years ago. Wow, wow, wow. How much has happened in between?
At that time we met, you were teaching a course in Atlanta, which I think became the source for your first book in 2003.
That's right.
And it's sort of interesting. So I come from a tradition, I mean, so my advisor, I guess, has written one book, but he wrote it late in his career. But I was a graduate student at Princeton, and there were a few faculty members like Eli Stein that wrote books, but there were many faculty members that felt that, you know, they should spend their time writing original research papers, and that they should leave to others the task of creating books. And I've really been impressed with the way that the books of Cedric and then later Filippo Sant'Ambrogio have really opened this area up to a huge number of people. And one of the other exciting things about the area is that it's thrown off tentacles in so many different directions. I mean, we heard about the connections to meteorology. It's also connected to Einstein's theory of gravity, as we learned only in the last couple of years, Riemannian geometry through the work of Cedric and others. So Cedric's advisor, Pierre-Louis Léon's, got his Fields Medal for work on the viscosity theory of solutions to partial differential equations. And I remember Craig Evans saying that, you know, he said that optimal transport has thrown off tentacles in more different directions than he'd ever seen, you know, including viscosity theory.
Yeah. I have to tell you, I once had a conversation with Tim Gowers, Fields medalist Tim Gowers, who told me that he had worked out a mathematically optimal way to unload his dishwasher. I should tell you that it was apparently his family weren't particularly best pleased about this. But I do wonder, actually, with all of you, you know, the field that you work in, do you ever find yourself applying it to your everyday life, as it were? Do you ever find yourself doing something like working out an optimal solution for emptying your dishwasher? Any of you?
It's very, very, very rare.
Tim Gow's on his own. He's on his own.
I'm sure there are some, okay, in the, let's say, there are some examples, there are a lot of examples in which you can apply mathematics in everyday life, and in the field of politics, it's good to remember that one of the founders of probability theory, I'm thinking of Émile Borel, was doing it also because he wanted to found decision theory, and his daily work in politics was also one of the things that he wanted to in which he wanted to put more mathematics into. But most of the people who apply mathematical reasoning in their life do it, say, on a fuzzy basis, not applying theorem. Just retaining the spirit of some theory.
That's fair. That's very fair, actually. You mentioned politics there, Cedric. I want to come on to that, actually, because we had an amazing question come in on YouTube from Herning Cheng. I'll bring this to you, Alessio, and then possibly get your comment too, Maria, if you don't mind. It's a very good question. They said, is it okay for mathematicians who do work in extremely, even though the world is in such crisis, do mathematicians have a responsibility to do more applied work to tackle these crises? What are your thoughts on that, Alessio?
Well, I mean, there are crises in the world, and I think, that's due to many things. But as mathematicians, we go on in our research, but it's not that we are not doing anything for society. So one has to think that, there are pure mathematicians and applied mathematicians. And the reality is that none of them exist without the others, in the sense that all the latest developments now, even for instance, artificial intelligence that is so fashionable now, it uses some of the results. It uses optimal transport in some aspects. So, so if there wasn't the pure math behind a lot of the applied developments, we wouldn't see what we had. So what I mean is that it would be stupid and, let's say, short-sighted, actually, that's the word, to just say, oh, we need to do something applied, because the reality is that applied research is happening all the time. And as mathematicians, it's not that if we all shift to applied, we'll make mathematics progress better. It would be just, you feel that now you have more work power, but on the long run, down in the road, 20, 30 years, you will have, in fact, less, I think, advancement, because reality, we go on together. I see, as I say, applied math use a lot of theorems for pure math, but at the same time, the fact that there are questions from applied math reach the pure mathematician. The pure mathematician think them from a more abstract viewpoint, and sometimes they can make discoveries that then have fundamental applications. So I think it's very good, and I like a lot the question because it makes a point, like, scientists need to help society. Science needs to work for the good of society and for the development, but one needs to be careful when one is too focused on the short-term applications, because then, for research doesn't work. I think for the development of research doesn't work.
Let me just change the question ever so slightly to come to you, Monica. I think that was very persuasive. We had another question that says, what hope does mathematics have to offer humanity in terms of the increasingly complex problems faced by civilization?
You never know. You never know. First, to tackle what Alessio has been, to build on what Alessio said, you never know in advance what is applied or not. You never know in advance what will be used to solve a problem or not. And if it's very sophisticated problems, maybe statistics will transform the many factor complexity into something simpler. Maybe it will be something coming from analysis, or who knows. I will, even though it's not exactly the question, but it's related to, I will build on the artificial intelligence example that Alessio was saying, and on my experience with it. When I chose my subject in mathematics when I was 20-something and decided I want to go in partial differential equations, I wanted the subject to have some applications. And I went into Boltzmann equation and problems about gas. Asking my PhD advisor right from the start, what are the applications of this? And it was very clear that this would lead me very far from the subject of artificial intelligence, which in that time was taken only by a few diehards of mathematical logic. And after I went into the subject of Boltzmann equation, I discovered that I was in love with the subject, not for its applications, but really for the formal beauty of it. I went into optimal transport because there was a connection between Boltzmann equation and optimal transport found by a Japanese researcher in the 70s. I remember Pierre Williams telling me, okay, it's fine if you want to study optimal transport, but does it really have applications? And in those days, it indeed seemed that optimal transport was very much in the theory. But much later applications came in. The first time I had discussion with the Canadian's most famous specialist of artificial intelligence, Yoshua Benjo, and I started to explain him what I'm doing. He told me exactly this. There's no need for you to explain me what you're doing. In the AI field, we've been studying a lot optimal transport these days, and we know how useful it is. And here, this is an perfect example in which a field that seems to be at the opposite of the application that you think turns out to have applications precisely in this field. And this is not rare. It's very, very common. And you never know where the theory will come from that will solve your difficulties.
Yeah, I think that's very true. I think that's very true, the real value of blue sky research. Maria, did you want to jump in on that question?
Yes, I agree with what Alessio and Cedric are saying. Also, my first answer about the responsibility that we have in this global crisis of the last years, my first answer is that I want to do my job as seriously as possible. That's what I'm able to do, and that's the contribution I can give in first seeing at this beauty that Cedric was mentioning, and in somehow bringing it up more and more. Yeah, and and then, as Cedric was saying, there are thousands of examples of things that were studied just for the goal of understanding them, and then turned out to have applications. I'm not maybe so much able to find these applications sometimes, even though there is a constant dialogue then with the people who work in more applied fields, where sometimes ideas come up and new problems are suggested to the more theoretical sides. So maybe I'm more from the theoretical side, but there are thousands of examples, and many of them are really everyday life, really. Like you can think at all the study of number theory that has been done and the way it's used now through cryptography, or in the way even bank transactions work. So, and these examples are really everywhere. And my impression is that somehow first we as a collective group, we understand how things work, we understand in depth them, and then the intuition and many other factors will bring up how to use them. Not all of them, but I was also very impressed in the way optimal transport is nowadays applied. I'm working myself on applications which regard quantum chemistry. It's something amazing.
Yeah, you just don't know where things will end up. I just want to pick up, actually, you mentioned there, Maria, you mentioned this idea of beauty. And I mean, this is something that you hear from mathematicians a lot, right? You know, and I sort of wonder if you are talking to somebody who is, let's say, only ever had the experience